let us review what we have done in the last two lectures, 21 and 22. We said that drainage conditions for a typical problem would be, I can have perviousness on the top, a sand layer, another sand layer at the bottom of the clay layer, whose thickness is called 2h. Thickness of the layer is hf, but we represent as 2h. If you do that, the mid plane is the plane that divides the drainage. Half the water will go to the top and half the drainage to the bottom. If you have one of the faces is impervious, that is, if the clay layer is resting on a hard stratum, rock, etc., whose permeability is very, very low, no failure, no drainage can take place, in which case the drainage path is equal to the thickness of the layer. So please remember this. And the initial pore pressure distribution, we can take any one, but most of the time we take as constant. But if you want to apply situations where the pore pressure can vary from top to bottom, we can also handle that. So the speed of drainage depends on the conditions at the boundaries. It can be one or two ways, and the pore pressure distribution initially can be constant or vary linearly. If it varies if it's constant, this is how, as I said, the consolidation or dissipation will take place. Initially, it will be all full, and over a period of time, the dissipation keeps occurring. This is the T is equal to 0, consolidation is 0, or the pore pressures are 100%, effective stress is 0. And then the dissipation takes place, and the effective stress or the degree of consolidation with depth is 100% at the two drainage boundaries and the least at the center. This is for time factor of, let us say, something like 0.8, 0.6, 0.1, 0.16, 0.2, 0.3, 0.4, and then slowly it gets somewhere 0.9 and it is. So what it means is the pore pressure first dissipates at the two boundaries and slowly it continues into the layer, and finally the degree of consolidation over the whole layer is equal to 100%. So this is how we get the equation. U is equal to sigma m, or I is equal to 0 to infinity, twice initial pore pressure, which is constant with depth, divided by m. M is nothing but 2 small m plus 1 into pi by 2 sine mz by h exponential minus m square t. Time factor t is CVT by h square, and U is called the degree of consolidation. We define it in this fashion. You can also say settlement any time divided by the final settlement, and you can write it as U, say degree of consolidation 1 minus sigma small m, or I is equal to 0 to infinity 2 by m square exponential minus m square t. For degree of consolidation less than 60%, it's a very simple equation. T is equal to pi by 4 times U square, or U is equal to 2 root T by pi. This is something you should be able to remember. Similarly, for, if I neglect all the other terms, for degree of consolidation greater than 60%, it's simply 1 minus 8 by pi square e to the power of minus pi squared by 4. So this is how the degree of consolidation may look like with respect to, and here is our degree of consolidation with respect to time for the whole layer, and you can see decreases like an S curve, reverse S curve, and here is the point I was making. You have a point of inflection. If I draw a tangent, this curve is to the left and this part of the curve is to the right, and you can see the consolidation is increasing with time, and this is on log scale, 0.01 or 3.01, 2.01, 0.1, 1, and so it comes up to here. So if I look at T90, it will be corresponding to that. It will be around 848. 50% is around 197. So this is how degree of settlement or consolidation varies with time t. If you now plot with respect to square root of time, I'm plotting square root of time, you get a straight line here, and then the curve decreases, becomes flat very easily. So if I define t as equal to CVT by h square, time is equal to time factor into h square by c. Okay, so now let's look at Taylor's method. You have taken the readings, drawn this graph, settlement or dial gauge reading with respect to square root of time in minutes. You have 5 minutes, 20 minutes, 40 minutes, 100 minutes, whatever it is. You plot square root of time here and you get this. What you have done is fitted a straight line and then drawn another whose slope is 1.15 times the slope of this line. It intersects here and then you take the time corresponding to T90. In this case, it works out to be square root of T90 is 18.4. So T is equal to square root of 18.4, and I go back to that equation to calculate CV. In case of log time method, if I now find out this graph and the asymptote is almost horizontal, the 50% will come somewhere here. Now this is a slight correction because when you plot with log scale, you will not start with T is equal to 0. There is no way you can get. The smallest value is a finite value. So you need to find out what is the settlement at T is equal to 0. And so what we do here is I take two small increments, T1 and T2, and whatever settlement between T1 and T2, I put it back, and this is where I start my settlement for 0. And this is I have drawn an asymptote and a tangent here. Wherever they intersect, I get the 100% primary. So using the experimental data, I do exactly the same. This is the initial value, and look at the tangent through the point of inflection, and I have drawn a tangent, they intersect, and whatever is halfway between corresponds to 50% degree of consolidation, and that is called T50. And if you know T50, you calculate T50 is equal to 197 h square by CV, or CV is equal to 19 square h square by T50. So this is how we calculate the coefficient of consolidation by Casagrande's method. Earlier one is called the Taylor's method. We'll go back into this later, but I just want to say in real life you will have three kinds of settlements. As soon as you apply the load, you may have some which is called volumetric distortion due to primary compression or consolidation and secondary compression or creep, whichever you want to say. There are three components. This will not be there if the load is very large. But if you have a footing, you have an embankment, finite size, you may get some volume distortion. And we call it sometimes immediate settlement for foundations. This is primary consolidation and secondary compression. And here is the plot. We were saying that even though 100% primary is over, the soil continues to deform. So this part beyond E100 or 100% compression is called secondary consolidation. And we define the slope of that as C alpha is the settlement over one log cycle of time. What is that log cycle? 1 hour, 10 hours, 100 minutes, 1000 minutes. Any one log cycle is whatever settlement is defined as the coefficient of secondary compression, and we use it to predict settlements. And this is very high for clays which are high water content. If the water content is high, the coefficient of consolidation, coefficient of secondary compression is high. For organic soils, it could be very high. For normally inorganic clays, it's only about 4 to 5% of CC. So we had to determine or use one of these empirical charts. And then we calculate secondary compression as equal to C alpha into H naught, which is the thickness of the layer, by 1 plus C naught, log 10 at any time T divided by a time corresponding to end of primary. So this is how we calculate coefficient of secondary compression, the time at the end of consolidation compression, that is whenever you want, and time of end of primary compression.